Previously, we ran a simulation and we learned how to make a heatsink with channels, a water-cooled heatsink with channels and hotspot. This is what we had done before, right? This is a previous example. Now, what I want to do is to modify this heatsink, and instead of having channels all across the heatsink, have fins where the hotspot is, because fins will create or pins will create a more cross-section area that's good for convection heat transfer through water. And then we can probably put these results together in a graph and see how the two heat sinks perform. So if I go here, the dimensions are the same. The only thing that's different, if I look at this, is that in the middle I have an array of 5 by 6 array of 1 millimeter by 1 millimeter squared pins with 1 millimeter spacing, and then I have an array of 7 by 1 millimeter squared walls or fins in here. Everything is the same, but I'm going to go over the process to create this model. Again, in the new window, I'm going to go into 3D, and again, this is a multiphysics problem. It's a conjugate heat transfer model, and it's laminar flow. So that would give me heat transfer with laminar flow in solids and fluids. I can add that and wait for it. Again, I have heat transfer in solids and fluids, laminar flow for the velocity of the fluid, and then I also have the multiphysics problem. Going to the next step, I can get stationary or steady state analysis. That's what I worry about. And now I'm in the main window in COMSOL. First thing I want to do is to change the units from units of length from meters to millimeters. I don't need to do that as long as I can take care of the values that I give in terms of meters. I want to create parameters like before. I want to have Tn for inlet temperature. I want to initially give it a 293.15 Kelvin for inlet temperature, and for inlet velocity Vn, I'm going to give let's say 0.1 meter per second to make sure that this is a laminar flow. So I'm not going to define parameters for the geometry. I'm not going to change the geometry. And then I want to come here in the parameter or the geometry. I want to create my geometry. Like before, for this one, I'm going to create the same polygon that I had done before and the same interior. The only difference is that I'm going to have to create these pins in the middle. So again, I have done my calculation, so I know the coordinates of the 5 points that create that polygon. So what I do here, the geometry, because I want to do a 2D model and then extrude it, so I have to create a work plane first. So I click on work plane. In the XY plane, that's fine. So I click on plane geometry, and then I create a polygon. All right, so the coordinates are going to be 0 and 0 first. Then the second one is going to be at 12.5, or actually 0 for X, and Y is going to be 12.5. Right, if I look at this, this is what I have. This is just a line so far. Zoom a little bit, right? Then I have to go 10 times cos pi over 3 in the X direction, and 12.5 plus 10 times sine pi over 3. And if I built this, this is what I get. Now I have to add 2 more points. So first one, copy this because it's the same wide component of the next point. Now the X direction is 12.5. If I build it, this is what I get. And finally, 12.5 in the X direction and 0 in the Y direction. So I do that, this is what I get. So this is the first working plane, similar to what I had done in the previous example, nothing different. And now I want to create the interior part, which is a 2 millimeter thick wall. So create another work plane. I've built this one, I guess I haven't, right? Do another work plane, and again in the XY plane, the same plane over there. Let me just turn this on or off. And in this case, again, I want to create a polygon with these dimensions, 2 and 0, so that I include the 2 millimeter thickness of the wall, and then I go to the next point. X is still 2 and Y is 12.5, and you see what I get. So this is that. Then I have to give the coordinates of this point, which I've done my calculations. That should be 10 times cos of pi over 3 plus 1, and 10.5 plus 10 times sine of pi over 3. So if I do build select, this is what I get. Now I have to go here, and I will complete it. So in the X direction, 12.5. In the Y direction, I have to give the same value here. And then finally, 12.5 in the X and 0 in the Y. So that will be that. So this is the interior. Now I have to create the walls or the fins and the pins inside the heatsink. So for the two walls or the two fins, I can create a rectangle. The width is 1 and the height is 12.5, and the corner is going to be at 3 because 2 millimeters here and 1 millimeter is the thickness or the width of the channel. So if I do this, I'm going to have that, which is basically one of these two channels. Again, I'm copying half of this or a quarter of this thing that you see. I'm going to do a mirror to get this half model done. Right, so I need to have another one of this right here, so I can do a model, or I can do an array. So let's say transform array, this one in the X direction 2, and the distance is going to be also 2 because the wall thickness is 2 and the channel width is 2. So that's going to be that. The next thing I have to do is to create, I come here, these fins, right? So there's going to be 2.5 in the X direction and 3 in the Y direction. The distance is going to be 1, 2, 3, 4, 5 from the X component, or from the X0. And then, so the first one is going to be 0.5 in the Y direction and 1 in the X direction. So I can do that. So let's go here, create a rectangle, 1 in the X, 0.5 in the Y, and then the corner is going to be at 5 millimeters 0 there. So actually not 5, 7, right? And then I can create for the rest of it. If I look at here, I have these two, right? So I can create this one and then make an array of that. So create another, this one is square, 1 millimeter. The X is going to be at 7. The Y is going to be 0.5 plus 1, so 1.5 in the Y direction. So that is this one. So let's make an array of this one twice in the X direction and in the Y direction. So if I do an array, and select the square, and the Y direction is 2, and the distance in the Y direction is also 2. So I have that created. The next thing I want to do is to create this other one array. It's 7 millimeters long and 1 millimeters wide, and the spacing is also 1 millimeter. So I can create a rectangle, 1 millimeter wide, 7 millimeters thick. This here is going to be 5 or 7, and now I have 0.5, 1, 0.5, 2.5, 3.5, 4, 5.5 I think is where it has to be. So if I click this, that's the corner, so that's where it is left. Now what I want to do is to mirror these 3 or 4 geometries, the 2 squares and the 2 rectangles, in the x directions. If I look at here, 1, 2, 3 times. So I can come make an array of 1, 2, 3, 4 items in the x direction 3 times, and the distance between them is going to be 2. 1 for the width of the fins and 1 for the spacing between them. So 1 plus 1 makes 2. And I get that. And if I click here, it seems like nothing happened, but if I say build all or build selected, that one shows up. Now I have the 2D base for my heatsink. What I have to do is to extrude them. Let's turn into a 3D view. And for that one, I'm going to say extrude. The first thing is the interior plane. Again, going back to my model, it should be 6 divided by 2, 3 millimeters in the z direction, and then the second one is going to be 10 divided by 2, 5 millimeters. So let's call this 3 and say build selected. Then I want to extrude the exterior part, work plane 1, 5 millimeters, and build selected. Now I have 1/8 of my model completed. Now I want to create that the cylinder here for the inlet and outlet ports. But before doing that, let's move this thing. Let me take a look at it in the XY plane. Let's move everything. Again, that's my preference to keep this surface at x equals 0. So select all. Move in the x direction by minus 12.5. That's half of the x dimension. Now zoom everything. All right. So create a cylinder. First thing, I want to make sure that the axis is in the y direction. Radius is 12 or 2.5, and the height is 5. So that 2 millimeters of that one comes inside the heatsink. The position in the x direction is going to be 0, and the y direction is going to be what I had for this polygon. So let me just copy and cheat from here. It's easier. So with that, and build selected. So that's where it stays. One thing I haven't done yet is the wall of this inlet outlet port. So let's come here in the array or in the layers, give a 1 millimeter thickness. I don't need to give in the bottom and top. I just only need in the sides. So if I build selected, those are built there. So I want to select domains and remove these. Now I have to do 2 partitions to partition this interior cylinder into 4 segments and remove the unnecessary domains. The first thing I want to do, come here to partition domain. This domain with the working plane 2, as you can see, it's perfectly selected. I don't need to do anything else. If I do build selected, you can remove this top surface. Now from the remaining domain, I can do another partition, and this time instead of work plane, an extended surface, and do, let's say, this surface and build selected. And again, I make sure that I'm not selecting a boundary, I'm selecting a domain. I can remove here. So that is completed. So let me also save this before I forget. Let's call this one Hotspot, and let's call this O2. Now what I want to do is to mirror this in the Y and Z direction so I can get a half model, and I can apply symmetry for this geometry. So mirror the entire thing about the Y direction first. I mean, I don't think it matters which direction you go first, but I want to go with the Y first, and I forgot to enable this, so now that's good. Then I can do another mirror and make this a full or a half model about the Z-axis. So if I do this, I have what I needed. So again, this is done. The only thing I have left to do is to define my chip, a hotspot, and the background. So for that, I have to create a work plane. in the XY plane, the distance is -5, so 0 is there. So if I say -5, build selected, it's at the bottom surface. And right here, I want to create a rectangle, 5 millimeters in the X direction and 10 in the Y direction. The corner is going to be at -12.5. Actually, this is going to be 12.5 in the X and 25 in the Y, because that's the entire chip. -12.5, put 2 dots there, and -12.5. So that would be the chip itself, but now I have to create a hotspot in the middle. So another rectangle. The hotspot is 5 millimeters in the X direction and 10 in the Y direction. That's because I'm doing a half model. And the corner going to be at -5, -5. So if I build selected, that's where it is. And all of the dimensions, if we go back to the picture that I showed earlier, is coming from here, that I had shown in the previous video as well. So I'm creating this chip with this hotspot in the middle. Right, so this is the model as I need it. So I can come here and say build all, and the model is ready. Let's save it as well. Make sure that it doesn't disappear. So before I move, again, like the previous video, I want to create some explicit definitions so that I can just select them in the previous steps, or in the future steps. So the first thing I want to create is for the fluid. So I want to hide some of my geometries for the time being. And before that, let's make sure that I'm selecting domains, not objects. So let's remove some parts of what I have and disable this. So first, explicit, I'm going to call this water and select where water is going to be. It's going to flow from here through here, here, and go out of my heatsink. So that is water. Let's remove this now for the next selection. I want to remove water, so it's easier to select the rest of my geometries. And this hiding doesn't delete anything, it just hides it from view, so I can select things easily. So next I want to do another explicit heatsink and do a domain selection, select all, or select box, and then undo the hiding, so I can also select these remaining domains. Right, so if I look at it, this is the heatsink body, and if I do a transparent view, this is the heatsink, and this is where the water is going to flow. Next, I want to define the inlet and the outlet. So this time it's going to be boundary, not domain. So I'm going to say inlet, and let's make sure that I'm selecting a boundary. Zoom in, and I'm going to select this and this. Okay, so let's create another explicit, call it outlet. And here, oops, again, I forgot that I want to make boundaries here and here. So that is the boundary. So now let's create another explicit, a boundary for the background. And another explicit boundary for the hotspot. So this makes life easier in the future, as I have to select things for these definitions. Let's save this. Now, before I apply materials, let's make some selections in here. Again, by default, everything is chosen as solid in the heat transfer in solids and fluids, which is not right. So if I come to fluid and from the selection select water, now everything that I had selected as water previously is going to be applied to the fluid heat transfer. And then there is this red mark that tells me that parts of my solid is overridden. So the heat transfer in solids does not apply to these overridden geometries. And in the fluid too, by default, everything is selected. So I'm going to clear the selection and say the fluid is only applies to the water domain. And now I want to redo this. Okay. Now that I have done this, let me save it. And let's go on and apply some boundary conditions and excitations. But before that, before I forget, let's apply the materials. Right click here and say add materials from library. From built-in, I want to pick copper for the heatsink, and then water for water. And that would take care of the materials properly. So that done, let's apply the boundary conditions and loading conditions. So first, I want to apply the heat flux to the hotspot. So I right click here and select heat flux, and I have to select the boundary. I'm not going to apply to everything, so I'm just going to apply to here. Sorry, what did I do? Might have made a mistake somewhere. All right, so let's do all domain. That was a problem that I thought I was in the wrong spot. Make sure everything is all set. Okay, right. So on the hotspot, I want to give a from the heat flux, I want to give a heat rate of 60 watts. And on the background, again, I want to go to heat flux, and the background, I want to give, let's say, 100 watts of power. So that's that. Then I can apply the inlet and outlet temperature or inlet and outlet boundary conditions for the fluid. So again, I can right click, go to the fluid flow condition. For the inflow, I need to give the temperature. And if you remember, I defined a parameter Tn. I'm going to apply in here for the inlet. I'm going to give Tn. And for the outlet, again, right click, go to flow conditions, outflow. And I don't need to apply anything. I just have to select the outlet. And the next thing I have to do, and I have to be careful here, is to define the symmetry plane, right? So if I right click here, select symmetry, and now just select the, let's look at it in this window. Then I can keep selecting the plane of symmetry. Just have to be careful, because if I select the wrong plane, then it could cause trouble in the calculations. So this is basically telling COMSOL that everything you see on the left is copied on the right. I'm not going to model it, but you take care of the calculations with the appropriate boundary conditions. So the equation is actually written in here. Now I'm done with the boundary conditions and the excitations for the heat transfer in solid and fluid. Now I have to go to the laminar flow and apply the boundary conditions over here. So the inlet is going to be at the inlet. The velocity is going to be Vn that we defined earlier. Then I have an outlet. I'm going to select outlet. I'm going to give the pressure 0. So whatever pressure I find for in the inlet is going to be the pressure drop. Then again, apply the symmetry. Let's look at it from the YZ plane. Right click on laminar flow and click symmetry, and then just select these surfaces. And then just to make sure that the multiphysics problem or portion is done completely. So these are the surfaces where solid and fluid will interact. So that's probably properly done by COMSOL in determining which boundaries are going to have the multiphysics or coupling. So the ones that don't have, which are the surfaces on the exterior of the heatsink, are not applicable for this problem. Right. So then I can save this and I can move on to meshing. Again, I have done this for different size of meshes, and I've done a convergence study before. And you can see that if I extend this window, it will show the progress of meshing. So you can keep with fine or normal. So I'm going to, let's say, keep it fine and build all. And then I can take a look at the progress in here, and it would tell me what is happening with the meshing of this model. It's going to take some time. So we can probably also look at the log and the progress. So again, this one is a bit complicated geometry because of the shape of the interior of the heatsink. And we have the pins and the fins and the channels and everything else. So it's a little bit more complicated. That's why it's taking a bit longer to complete. And of course, the simulation is going to be nonlinear. So the convergence study can take some time and all that. So I'm not going to start the simulation here or the computation because it would take a few hours. But I'm just going to show you how you can start a computation. So once it is done, we can see our model. See very fine mesh over here because of that fins and pins and everything else. And if you look closely, it shows us that the mesh is done properly. So the nodes are meeting. So with that done, the next step would be to define the study. So if you want to just run with these parameters, we can just click here and say compute. But if you want to do a parametric sweep, you can right click on the study and do parametric sweep and then define parameters, right? I can add a parameter for temperature or velocity. Let's say for velocity, I want to go from, oops, I deleted that. I want to go from 0.05 meters per second at every 0.05 meter per second step, and the final velocity of, let's say, 0.2 meters per second. I can say add, and this is for, of course, velocity in. Then I can add for temperature, I can go from a range of 283.15 kelvins to, at every 10 Kelvin step, to 293.15 kelvins, and can add that. And then I can say run for all combinations so that it would run for 8 different, or I guess it would be 8 different combinations. Then I can say compute. It will take a few hours to compute this one. And you can see the convergence plots as it goes through, and it will show you all the steps and the progress in this window. But again, because it will take so long, I'm not going to start the computation here. I'm going to save it. I'm going to open the one that I have done earlier, this one, which is basically the same simulation. So if you run it, COMSOL will give you some results. The temperature, as you can see here, the bottom half temperature. Let me extend this. So let's, like the previous video, I'm gonna remove some of these results, and then I want to show you how you can get these yourself. So I'm going to remove the data sets all the way from here to here. And then also want to remove the derived values and the table, right? So once you're done with the simulation, this is probably what COMSOL will plot for you. But now we want to get more plots out of this. The first thing I want to do is to come to component and first select domains and remove some of the top domains. And if I look closely, I can remove some of these. And the reason I want to do that is I want to be able to see what's happening inside the heatsink in terms of velocity, in terms of temperature inside the heatsink. So I have everything that I want. I can zoom all. Then I can create a database, which the results will be shown. I'm going to select surface. And I want to say select all with that box. So this would be the bottom half. Now I want to mirror this bottom half so I can have like a full model, although we didn't compute for the full model. So I can come right click here and say mirror 3D. My data set is going to be the bottom half and in the YZ plane. That's okay. So if I do that, I'm going to have this domain, although I did not calculate for the entire thing. I'm going to call this bottom half mirrored. Next, I want to select boundaries on the bottom surface, which correspond to the chip. So let's select in our database, surface, come here, this, 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 and this. I'm going to call that chip. And also I want to make that mirrored. So a mirrored 3D with a data set of chip, and call this chip mirrored. Okay, so I have the databases necessary for my next plots. Let's say I want to see the temperatures in the interior of my heatsink. So if I can come to results and I want to see a 3D result, and let's remove this transparency. I don't know where it is. Okay, I don't know why it's, all right, that's okay. I don't need to worry about that. My data set is going to be bottom half mirrored, and I can select the variations of my inlets and my inlet temperature and inlet velocity, whichever I want to plot. Let's say at 0.1 meter per second. And for that, I want to do a surface temperature. So when I click surface on this 3D plot, it shows the temperatures, right? And it shows the temperature in Kelvin. I can change it to Celsius. So now the temperature is at around 140 and 20. So 20 is the temperature of air or water coming in, and I can see the temperature in the bottom surface. I can also say, so let's say this is bottom half temperature. Then I can do a bottom half velocity, which will not include the velocity in the solid, because the solid is not moving, but I don't have to worry about that. COMSOL, I shouldn't have done this. COMSOL is smart enough. So I just click result. Again, another 3D. Again, I want to do bottom half mirrored. I can change or select the combination of temperatures and velocities I want to plot for. Then I do surface plot. At this time, instead of temperature, I want to come to laminar flow and change or select velocity field. So I click on this and it's changed. If I plot now, it shows me the velocity. As you can see, the solid is transparent because of course there's no velocity in the solid. It shows the velocity in the interior of the heatsink, the velocity of water. So we can see that over here as well. And let's call this bottom half velocity. And I can change it to, let's say, 2 meters per second or 0.2 meters per second. I can see the difference in the temperatures. And let's take a look at it like this. Then we can also see the temperatures on the chip. If I wanted to do that, I can say, go here in the results, give me a 2D. I think that 2D should work. Bottom half or the chip. No, I don't want to do the chip because it's not 2D. So I want to delete that. I'm going to go back to 3D results and check chip mirrored. And again, I want to do a surface and temperature is fine. So I can plot the temperatures on the chip. So I can see the highest temperature are in the background, and the lower temperatures or higher temperatures in the hotspot, and the lower temperature are in the background. And these are in kelvins. I can change it into degrees Celsius, and you see the temperatures we get in here. So 95 about is the temperature on the hotspot. Now if I wanted to find the maximum or minimum temperature of the chip, I can come here in the derived values, and I can say, give me the maximum on the surface. And I don't know if I can select chip. Okay, I can select the, no, I didn't define the chip as over here in my parameters. So fine, I don't need to do that. I can select as these 4 surfaces. So give me the maximum temperature in degree Celsius. Then give me the minimum temperature of the same surfaces. So if I right click on derived values, I can come to minimum on the surface. I can select these 4, and I can say temperature in degree C. And then I can also get the pressure on the outlet. Let me make sure that I'm on the right. I think that one's the outlet, but I'm not sure. So if I come to my definitions, the outlet is the other one. I'm looking at the inlet. So this is the inlet where I want to find the average pressure. So let me actually bring back everything. And on this surface, I want to find the average pressure on these two inlet surfaces. I think if I do P, that's fine. Right, so now I can go on and evaluate them. So the maximum temperature, evaluate on a new table. So it shows the maximum temperature. So the 0.05 millimeters per second velocity is really not great. And then I can evaluate that minimum temperature on the same table. So I can see them all next to each other. And then I can evaluate the pressure drop right in the next column. Then I can take this into, let's say, a CSV file and call it another, like this one, call it 0.02 or 02, right? Or whatever name you want to give to it. And then if I go to that folder, I can find this file. If I open it, see those values. And I can play with this in Excel and MATLAB and make 2D plots and compare the effect of inlet velocity and the inlet temperature and my heatsink for this analysis. And these are the temperatures of the chip and the pressure drop. So it can tell me what is happening with the model. So what you see, for example, if I wanted to play with this a little bit, if I wanted to look at some of the values, for example, I can copy some of these results for 293, I think, and these stuff, and maybe copy it in the next table or next sheet, and then I can just basically do I haven't selected anything yet. Do a scattered. If I can find the scatter over here, pivot chart. For some reason I cannot find the scatter. All right. Oh, it's because I have the same temperature, right? So I should find the right values for this. I was thinking like why it's not giving me the correct plot. So if I do this, then I can make a plot, a scatter plot, and it can show me that as the velocity increases, the pressure drop is also increasing. That's something I can take away from this simulations. So in this example, we went through a model of a heatsink like this that we saw earlier, but we replaced the entire channels of some of the channels with pin fins to see the effect of pin fins on the hotspot, which is in the bottom of our heatsink. Or yeah, that's where we have higher power, and in the background we have lower power. So we also examined or learned about doing polygons, symmetry, conditions, arrays and mirrors, and COMSOL simulations. And we did some post-processing. I hope you enjoyed this video, and I'll see you next time.